Quindi posso iniziare? Allora, buongiorno a tutti. Come prima informazione vorrei dire che parleremo in inglese da ora in avanti. Se qualcuno vuole comunque fare un intervento in italiano, per chi ci sta seguendo su YouTube nella chat, ovviamente è benvenuto. Welcome. I just mentioned that we will be talking mostly in English, given the presence of our guests. And I am Giovanni Indiveri from the University of Genova and ISME that I will tell you about, and the colleagues sitting here with me at the table will be introduced very shortly. So let me start briefly to mention our gratitude to the organizers for this seminar. So the Genova Blue District people that are supporting us in all the organization, including but not only with the infrastructure we are using today for this meeting. So I'm really very happy of having had this chance, and it's thanks to them that we are here. The idea of today is to discuss and present the status of the art on marine robotics. And in order to give an overview about the situation, Massimo Caccia and I, thought of inviting a number of people who are absolutely on top of the research and the both academic and industrial sides, who will allow us to get a better understanding of the situation. So let me skip to the second slide. I would like just to say a few words about the moderators. I already introduced briefly myself. Giovanni Indiveri. I'm associate professor in controls and teaching robotics. And Massimo, who is here next to me, is the other organizer of this event. He is affiliated with the Istituto di Ingegneria del Mare. I don't know, Massimo, the English for it?
Yeah, Institute of Marine Engineering.
Okay.
Of the National Research Council in Italy.
Okay, I don't know if you want to say a couple of words. It's probably on already, I think.
Is it working?
I think so, yes.
Oh, okay.
Okay.
Thank you very much to Giovanni and all the organizers of this event. And as Giovanni already mentioned, I am employed at the Italian National Research Council now for almost 30 years, and I always focused my research in marine robotics with a research group that design, develop, and operate underwater and surface vehicles without men on board. And now I think that, Giovanni, you can go on introducing other speakers.
Of course, in fact. So you see the list here. We have, I will show you the timetable of the presentations in order, let's say, of talks. We have Vladimir sitting on my left. He is the CEO of a robotics company in Croatia, H2O Robotics. I have a short video that I will show you in a while. Antonio Pascual, sitting on my right, is professor of robotics at the Instituto Superior Técnico in Lisbon, Portugal, and he's been doing research in this area since long. And you don't see him at the table yet, but he's sitting just in front of me. Alessio Turetta, who is a business development manager from a company Graltech that is located here in Genova, and that is one of the leaders in the field of autonomous robots for marine applications. The timetable of the presentation is here. We hope to be able to stick to it precisely. So the first talk will be by Vladimir. approximately 30 minutes. This includes some questions at the end of the presentation. And here you see a short introduction of Vladimir himself. So he studied and worked for many years in US in autonomous marine systems, and also more recently in autonomous driving cars. I will skip all the details that you can probably read on the slide. I would just like to mention that since a few years he came back to the old continent, and he is now leading this spin-off company. I think it's a spin-off, right, of the University of Zagreb in Croatia. The title of his talk is Innovative and Cutting-Edge Marine Systems and Technologies. Then, after his presentation, we will have a talk by Antonio Pasquale on cooperative motion planning, navigation, and control of networked robots for scientific and commercial operations at sea. Antonio's CV is also reported in the slide. He has a very long experience in several institutions, beginning with the IST that I mentioned earlier. He also has an appointment with the National Institute of Oceanography in Goa, in India, and he has been responsible for many years of the Technical Committee in Marine Systems of IFAC. He is a very active researcher, and I think many of you actually know him already. Let me thank both Vladimir and Antonio for having accepted this invitation that was not obvious, given that they traveled in this time that is still a little bit critical, as you know. Last and not least is AUVs for seismic surveys, the title of the talk of Alessio Turetta, who I know since many years, and he has also been working in the field since he graduated, academia, it's nice to mention that he has had the two experiences from academia first. He worked at the University of Genova for a number of years, actually, and since some time by now, he moved to industry and is one of the leading researchers of Graaltech, as I mentioned. They are doing very much applied research and work, and it will be, of course, a pleasure to listen to his point of view. In the afternoon, after these three presentations, Massimo and I wanted also to share a little bit of our own experience in the field. So I am currently the director of ISME, that is an institute, Integrated Systems for the Marine Environment. It's a network of universities working in this area, and this is what I will be talking about at the end of the schedule, the works. And before of that, Massimo from CNR will give an overview of their activities that are, of course, also extremely important and well known from the Institute of Marine, sorry Massimo, Istituto di Ingegneria del Mare. I keep forgetting the English, I apologize. Okay, as I mentioned earlier, if there will be any question, I think it's no problem either from the floor or from the people connected just to interrupt us. Unfortunately, I do not see in real time the chat coming from YouTube, but the organizers have told me that they will take care of this. So if you have from remote any question or any concern you want to turn to us, please go ahead on the chat and we will receive a note from the organizers. From the floor, just raise your hand and it will be even easier. Okay, that's all on my side. I would leave the floor to Vladimir.
Thank you, Giovanni. Okay, Giovanni already introduced me. Just want to say that I'm honored to be here. I'm glad that I was able to travel after a long time. I'm sure everyone else is excited about hopefully being able to interact in person with colleagues, other researchers, and friends. I want to say a couple of sentences in Italian because I lived in Italy for 5 years. Grazie Massimo, grazie Giovanni per invitarmi. Io sono molto contento per essere in Italia. Sono stato in Italia, ho vissuto in Italia per 5 anni e ero contento ogni giorno in Italia. H2O Robotics. It's a small spin-off company from University of Zagreb, and without further ado, we'll go and start. So first I'll say a few words about the company and then products that we have and how we actually arrived to what we think our best shots at the market are. So 2017, founded in Zagreb, Croatia, spin-off from the university. Many of the people here in the room and maybe some in the audience know Professor Zoran Vukic and Nikola Mišković. They are the founders of the company. In 2017, they asked me to join. At that time, I decided to work on self-driving cars, but now I'm back. I'm back to my roots, and we specialize in marine systems, robotic systems that are used in the marine environment, and also some subsystems that we think we can have meaningful and interesting and sellable products. So initiation of the company, 2017, 18-month effort. I want to share this information with everyone because sometimes businesses and companies, they don't necessarily have time to look around for public funding. But even a little bit of public funding can help you. And that's how this adventure started. So 18 months, 100,000 euros, you don't think it's too much, but it was enough to turn one prototype into a product. This prototype came from the European funded effort called CADI. Antonio here was a part of that effort where it was essentially about robotic systems that interacted with humans. So human-robot interaction applied to diving. So underwater vehicle that was a dive buddy to the diver, able to help the diver, bring some tools to the diver, or guide the diver to a specific location. And a surface vehicle, and we'll talk about that product first, that was there to be able to provide connectivity with the operators that might be on shore or that might be anywhere in the world. Nowadays, you can do that with the GSM system and the cellular system, and also safety. So any diving operation requires divers to be marked for safety reasons. And this small autonomous buoy can be serving that purpose as well. So that APAD, the ASV system, turned into the H2 Omni X. All our products have this H2O, as our company is called H2O Robotics, and we start with H2O. And all our products, some with Italian names, you will see, start with an O. So product that we started selling, as I said, and made a product from a prototype was this surface vehicle that is fully actuated, can do the dynamic positioning on the water surface in certain sea state, not unlimited, but up to sea state 3 at least. We have also H2O Observe system, which I will talk about, and that is a low-cost acoustic underwater ranging and a communication system. I'll touch upon a little bit about underwater localization and what ranging means, but basically you have ability to obtain the distance from one asset to another. The orologio H2 orologio is our prototype technology, and electronic boards are pretty much the same, but the packing is a little bit different. You see here, it's packed in such a way that it can be on a human wrist, and it also works with the diving watch. So basically, we utilize the advances in technology because nowadays you can install applications, like on Android phone or iPhones, you can install application on diving watches. So user interface is via the diving watch, and then the acoustic and the rest of the hardware is on the wrist of a diver. This is the H2O Robotics Observe. So we also provide services, research and development. Basically what we want to do is 25% of the current customer that we have for this product that is a valued customer of ours, 25% selling this device commercially, 25% public funding, EU and other agencies, and 25 other markets. I'll also talk about other markets. So just recently we sold 2 of these systems to University of Dubrovnik in Croatia. That one had above water camera and below water camera. But the surface vehicles in general, and generally robotic vehicles in the marine environment, have some kind of propulsors, in this case 4 propulsors, and then power boards and batteries, PCs of course, that can process information in real time or log the data depending on what your mission is. Our system is modular, so we can add different equipment. Here showing the above water camera, below water camera is not visible, but it's integrated. Different sonar systems, and also we showed the multiple robots cooperating, working together. Nowadays very popular is this robotic operating system as the middleware for the software that is hosted on the platform. So applications for this can be the surveys of, in this case, coastal areas, ports, harbors, and you can do that with acoustic system, so sonar systems to obtain bathymetry, information about the terrain below the surface vehicle. You can obtain 2D or 3D maps using the sonar systems, or you can do the same thing with the optical systems. From these pictures that come from video camera, you can do some reconstruction using software tools in order to obtain the third dimension. Also, that's something that you can do in post-processing. In some cases, with using graphical processing units, you can do that in real time. There's many different interdisciplinary components in marine robotics. So artificial intelligence, which is very popular nowadays, popular term, many different models for detection, classification, different objects can be applied to both sonar data that you see here on the left, or camera data. In this case, for this particular platform, we have integrated different forward-looking multi-beam sonars as well as side-looking sonars that you can see here. So I'll break the presentation a little bit with the 2 robots working together in Biograd, which is a city in Croatia, in south of Croatia, where we have this interdisciplinary training every October, and it's going to happen this October at the end of September, beginning of October. Anyone that is interested, Breaking the Surface is the name of it, so if anyone wants to come. So here you see the ability to follow a specific trajectory, as well as to do dynamic positioning by 2 robots. Right now, they're just pre-programmed to go to a specific location using their GPS and INS systems. So global positioning system you can utilize it when you're on the surface. I'm sure that Antonio will talk about some other ways to navigate underwater without GPS. But here we do use GPS, but the idea is to be able to precise position in some areas that are close to the coast, that are confined, that you don't want to touch objects around you. And then also do dynamic positioning in order to support diving operations or any other missions. So just want to say that you can ask any questions along the way during my presentation if you're interested in a particular subsystem that I showed. H2 Observe, it's a small unit that consists of an acoustic modem, and our collaborators from University of Newcastle in the UK, they have developed this technology. So what we used is we packaged that technology together with our electronics and make a self-contained standalone system that can be used as an underwater marker. So you can mark an object underwater, leave this unit, and then come back to it. That might be interesting for some archaeological site, for example. Also, it can be connected to an AUV, and it can be wirelessly connected to an AUV. Alessio will talk about their AUVs, but in this case, you don't have to have any connectors, any penetrators. As long as you have a Bluetooth chip inside of the AUV, we can talk to it, and we can pass the information from the AUV to the surface. The unit shown here is the integrated unit with the tablet. It's Android tablet where we have our application, and that unit can be lowered from the boat and talk to the unit that is submerged. For a customer in America, we integrated a specific system that is, the form factor is matched to what they needed. So as you saw, Orologio has a specific form factor to fit on human wrist, this one on their AUV. Also, we have several prototype systems that we have the Bluetooth connection between so in this case is the cable connection between the unit and the tablet, and in this case is the Bluetooth. So a diving operation can be performed where you just attach with a carabiner, which is commonly used for boating, this unit to the boat, and you talk to the diver using our app. So different applications for it. What we are trying to target is the smart city type of applications. Nowadays, very popular term is Internet of Things. All the devices that are connected, even home appliances, smart homes that you can turn on, your dishwasher or a heater before you come to your house, something like that, but we want to do that with the underwater world. So we want to connect different sensors, autonomous vehicles, divers, be able to have the connectivity at all times using our sensors and the terrestrial networks. And in addition to that application, in some situations, it's very useful to have such devices be deployed in the field and be able to pass some information, because we noticed that deploying this device from the boat is easier than taking our surface vehicles to do some measurements at sea. So we could be attractive partners for some projects that are going on both in academia and industry. I'll show you how we do the connection with the smartwatch. So smartphone in this case, sorry. So our application runs on a smartphone devices, and we have our unit that is H2 Observe. And you can basically have the unit connected with the electronic piece that you do not have to make waterproof, because only splash proof, because it's still on the boat. That establishes the Bluetooth connection with the smartphone phone, and the application is being used to send messages and receive messages from underwater. So again, either autonomous underwater vehicle, some sensor information, or a diver. H2 Orologio is the, so basically when I joined the company had this H2 OmniX as a product. But I realized that the production and of autonomous surface vehicle and even selling it is a difficult thing to achieve. Usually you have some ability to sell to internal network of colleagues, but we wanted to do a subsystem and make it commercially available. So we noticed that there is a system that is commercially sold that looks like a dive computer, but it's also equipped with acoustic modem. And we thought about, having our technology, but instead of building the whole dive computer, using the dive watch or smartwatch that are now readily available for diving, running. They have some, ability to go underwater. In this case, this is Garmin watch, and using it with our technology. Also, on the other side, on the boat side, there is a big Pelican case, big suitcase with the electronics and acoustic transducer. In our case, it's the cell phone that you commonly carry, installing our app and using the device that we have. The first prototype for our H2 Orologio was made with the utilization of 3D printers. But then, this is an important thing to say, that along the way, you try to be innovative, not only about trying to do some new products, but then also the way you produce things and the process improvement. So from the printing, we saw that takes, it's not a easy form, and it takes a long time to print. So we made this silicon, after we did the dummy unit and 3D printed it, we made the silicon mold, and using the silicon mold to make a first prototype of the unit, because we put in silicon mode together with electronics, we put polyurethane, which is the substance that gets hard and at the same time protects from the from pressure and from for underwater usage. So this slide shows a little bit about a utility of potentially H2 Orologio as a product, and the diving buoy as with electronics in it. So you have an acoustic link between the diver and the buoy, and then you have the GPS, GSM, ability to communicate with the boat or with the rest of the world. So many of these technologies exist nowadays as a piece of the Garmin portfolio of products. Garmin has been traditionally known for, as a manufacturer of these units that we used before cell phones for navigation, and sometimes they were rented at the rental car agencies. But with many of these different products for outdoor activities, we think that the augmentation of our technology with Garmin technology can be a way to go. So we're in the process of talking to them. So to show you also the way you communicate with the boat, you have the essentially two of our products working together. One, H2 Observe, that is connected with the cell phone or with the tablet, and I showed you that movie before. So first you disconnect the unit, place it in the water, establish the connection with Bluetooth, and then you can communicate with the diver. Not only that you can communicate, be able to send text messages that are user-defined, by the way. So depending if it's a technical dive or a commercial dive, recreational dive, you can have different messages. So this is a true, not necessarily a cell phone because you don't have touch screen nowadays, but it's an underwater pager that you can send different SMS messages. Just to show you a little bit of, it's an important thing about this technology is that it should work up to certain distances. It does not have to cover long distances. The diving operations normally are being used within a few hundred meters. We did a test last year in a very shallow water environment with the H2O Observe that was installed on one of our H2 Omni X robotic surface vehicles, and 3 of them placed on the bottom. And we were able to first, this is the initiation of the mission, where all of them get good ranges. And then after some distance of about 400 meters, you have a little bit of a gap, or either the vehicle was moving too fast or the acoustics were not favorable, and then you regain the acoustic messages again. It's important to just say that acoustic communication channel is low bandwidth, and also there are a lot of reflections, but the technology made by our colleagues at University of Newcastle is satisfactory for being able to communicate and then also localize. So also our depth rating, I told you a little bit about how we make our products with silicon mold until we established, a final design for all the applications. Silicon mold, and then putting it in a polyurethane. Technologically, manufacturing project is not very easy. People here know about deploying things at sea. It's not very easy to make technology that can pass that harsh environment. So here is the test that we did with 2 of our products, Orologio and Observe, up to 100 meters of water depth, and that successfully passed. I'll finish my presentation with a few things, basically lessons learned from our journey. And when you think about innovation, anywhere in the room, what is the first thing that comes to your mind? Anyone? Okay, so I'm sure everyone, at least some people in the room, thought about something new, original, improvement, disruption, novelty. All these words are connected to innovation. So innovation is something that is very important. And I want to stress about the innovation being a must for every organization nowadays. Even some terminology in today's business is that in addition to Chief Technology Officer, CEO, you have also Chief Innovation Officer. Something that goes along with your business strategy, but maybe it can be a little bit disruptive and can actually benefit the company and turn it, maybe steer it temporarily or for the whole way in the new direction. So it's something fresh, but it can be also product or process. It does not have to be a new product, but process. I talked a little bit about that, how we, thought, based on the experience of others, using at first 3D printing, but then we saw the limitation of it and decided to make these silicon molds. Also, the innovation happens when you engage all the individuals. A power of spin-off that is linked with the university, and that's something that is also, I want to encourage people in the room and maybe in the audience to not be afraid. It's very useful to have and to stay in this environment because you can engage many, many smart people in innovative thinking. Reverse mentoring, so both that the junior people and senior people can the mentoring goes both ways, and permission to experiment. So by allowing some engineers to spend some time and not necessarily pressuring them, we were able to achieve some things in a short time. Open innovation is something that is also important for us. It's important for us to look for others. So maybe at first they will look or appear to be as competitors, but they can actually become partners. And we use external resources. So anytime we sell a system, we actually seek customers' feedback and be able to improve. So for instance, for this system that we're working on right now, this product, we have created a prototype for our buoy system. And although we have a lot of lessons learned from H2 Omni X, it was not very easy to create this robotic system for the, to support diving operations and also to make it affordable. So we're teaming up with an Italian company that we found their design of a buoy system that their system is called go up buoy. So basically it's used to mark fishing traps and other objects on the water, but it stays submerged, so it does not represent a hazard in the marine environment, and also the object that you want to leave behind, it's not going to be easily found by some other people. So what they have is this, they have a small acoustic link between the buoy and the boat. The boat is using just its mezzo marinaio to put the acoustic transducer, and the buoy comes up upon the remote command. So what we're working with them right now is to put our technology, our electronics, inside of the empty space of their unit and be able to have ability to show our technology with the system that is already on the market. They already have clients, customers, and at the same time they are working on the ability to not only go up, but also an active system that pulls the buoy down. So it will be a vertical profiler, and it can be utilized for environmental monitoring, which is what the goal of this project is. Thank you very much. Any questions?
Yes. Thank you, Vladimir. You were perfectly on time. Actually, I confirm we have a couple of minutes for questions from the floor. Two of them. Yes, first.
Go ahead. Yes, it's Bluetooth. So Bluetooth is something that works in air, probably up to 10 meters reliably. Underwater, you have to be connected basically on top of each other in order to work. So there's no, there's very, very poor connectivity when you are even a centimeter off. So basically, Bluetooth device that is in Garmin watch, we place the Garmin watch on top of our device, and that's how they communicate. And divers communicate with each other using acoustic signal. So basically, RF signals are attenuated underwater. That's why GPS does not work underwater, but acoustic communication is being used for communicating underwater. The electrical signal is transferred to this ceramic transducer that vibrates, and that's how the signal is being sent. With the low frequency, you can even communicate from here to across the world.
My question was actually related. Can you hear me?
Yes, I can hear you.
Thank you very much. So, it's related to the bandwidth for the transduction between electronic signals and acoustic signals. So, can you tell us more? I mean, I'm not in the field, so I would be interested in knowing how much time you need to transmit a certain
Yeah, so in one of the slides, it was 2 hertz is turnaround, like every half a second you can transmit in distances that we're talking about of being 500 meters, 100 meters. So it's not instantaneous. And then also bandwidth is 450 bits per second. So 450 bits per second, definitely not enough to send images, and but to be able to send this small textual messages, it's adequate number of bits. Go ahead.
How many devices do you support with the H2O service? So how many more logic can you query?
Right now, with the current technology, 256, but that can be changed as well. Any other questions, anyone?
I have a small curiosity. You were mentioning you can use these devices for localization because you measure range, right?
Correct.
Okay. I guess you measure range with the time of flight?
Correct.
So the questions are two. First is whether you have issues with synchronizing the clock, so if this is a problem or not. And then the second question is, if you have one range only, that's obviously not sufficient for localization, so...
Yeah, so that's a very good question. So basically the, two-way ranging being used. So
Okay.
you basically open the counter, the message is sent and received, the speed of sound in the water is known, and you get the range from the asset that you're communicating with. The ability to install precise clocks and to synchronize them before they go underwater with, let's say, GPS time is another possibility.
Okay.
We have not done that just because there was no need at this point for that, but definitely, like, if we want to have what we talked about, like many different units, the one-way ranging and being able to have a sender send a message and multiple receivers receive a message and obtain, by the virtue of receiving a message, knowing the range from the sender is something that is important. So that's one answer to that. The second, I believe, was for localization. Yes, so for localization, we are definitely in a need of having either on this small surface vehicle 2 transducers, because of this small surface vehicle, that would be about half a meter apart. So it's called short baseline system. It's not very easy, it's not known yet that it would work well, but 2 at least. But with these 2 buoys that we are planning on using, so basically to have a dive boat deploy a set of divers and deploy 2 buoys instead of 1, we'll be able to localize with the same technology that is commonly used for autonomous underwater vehicle, which is long baseline system.
Very interesting. Thank you.
Sure.
Thank you, Vladimir.
All right. Thank you, everyone.
Thanks again.
Yeah.
Okay, so according to our schedule, we should now, let's see if you can take this. Antonio Pascual, that I introduced earlier, will present a talk on cooperative robots, scientific and commercial applications. Antonio, the floor is yours. Yeah, you're online.
Okay, let me just time this thing.
I can keep track as well.
Okay, good afternoon. It's truly a pleasure to be here. And I have worked for so many years with many of the people here, so I am with them very often. So I'm going to talk about a team that I shouldn't say it's complicated. I mean, it requires some work to do these kinds of things. You all know that. But I would also like to give you sort of a historical perspective of how everything started. So we'll see. I'll have too many slides, I know, but I'm not worried at this point. Okay, so I come from the University of Lisbon in Portugal. It's a big school that brings together not only engineering, but other things like law and medical school, so on and so forth. And we have wonderful dual doctoral programs with the MIT, CMU, and EPFL. So whatever I'm going to talk about it here is based on the work of many, many people. So I'll focus, for example, on the MORPH project. So I'll focus on European projects. Also on the WeMast project that was coordinated by Giovanni Indiveri. And also there's a project that is going on, which is an infrastructure network coordinated by João Sousa in Porto, that brings together many of us to afford commercial companies and higher scientists access to infrastructures to carry out their experiments without spending too much money. So, how did I start working on this? I'm sorry for those of you that have seen these slides, but then I'll move on. Well, I started by being interested in the cooperative operation of vehicles, underwater and surface. And at the time, I knew much less than the little that I know now. And I was quite taken aback when I was told, look, to communicate between an underwater vehicle and a surface vehicle, it's a problem because you have all the multipath effects, okay? So communications are extremely hard underwater because of multipath and many other things. So we came up with the idea, this was 2000. I think Pino was one of the reviewers of this proposal, I don't remember. Why not transmit in the vertical? You avoid the multipath and you bump up the baud rate. And that's what we did under the European project called Asimov, and this was long ago, 20 years ago. So here for the first time I was confronted with the need to operate a surface craft and another underwater vehicle in cooperation so that the top one would ride the bottom one. So one of them would be the leader and the other one would be the slave. This proved to be difficult because at the time we didn't have ROS, ultra-short baseline systems to measure relative positions were still big and huge. The same with communications. I remember the acoustic device we used was in a cylinder of this size. I mean, it was a nightmare. So we did some, but not to our entire satisfaction. But then things changed completely. Around 2010, when we had access to small embedded processors and all beautiful switches and sensor switches, new acoustic and optical modems, positioning systems, and the paraphernalia that comes from network control and navigation and planning. And for those of you that are studying now or initiating our degrees, this is a never-ending story. I mean, there's so much to do along these lines. So it's really beautiful and challenging to put together the theory and the practice. So I'll start with the first project where really we crystallized the concept of network systems. And this was the MORPH. It ended in 2016, Cooperative Marine Robots for Marine Habitat Mapping. So the idea is the following. The scientists told us that when we do these maps of the seabed, okay, fine, we can do them. But it's far harder to do maps of vertical walls that can extend over large depths. And you have to find out what is there in terms of fauna and flora. And you cannot use a classical boat because it's too close to shore. So we came up collectively with the idea of developing a big vehicle, virtual vehicle that consists of putting together a couple of vehicles. So one at the surface that does the navigation, it knows where it is. Then some vehicles in the water column playing the role of anchors, also trying to find out where they are, and also looking ahead with sonars and things like that. And then a bunch of slave vehicles that are connected to this virtually and map the seabed. So that, and then there's a dance underwater because they progress, and as the wall is detected, they move. And then even there's a negative slope on the wall. One of them has to coil back in order to maintain the transmission. So it was a beautiful project where we had actually the vehicles had to communicate and establish a network for communications, controls, navigation, all kinds of things. So there were many partners involved. The coordinator was Jörg Kauger from Germany. And we did this successfully, and we ended up Massimo was involved in this, and we ended up with the final mission in the Azores. So this is not the final mission because I want to simplify our life and not show anything extremely contrived. But let me see if I can go to 2 or 2. It's difficult. Yeah. So you see here you see a bunch of vehicles. There are 1, 2, 3, 4, 5 vehicles. The top one knows what it is doing. The other ones have to learn on the fly. Here we were still using the umbilicals for protection, but then we cut them. So you see all of these vehicles are coordinating underwater, finding the relative distances, establishing a formation, communicating while other vehicles take snapshots and build mosaics of the seabed. So to me it was a beautiful and wonderful project. It required a lot of effort, and to make things work it took a long time because we had heterogeneous vehicles, so we had to come up with ways of putting everything together. So it was a beautiful example of networked control and navigation. So in terms of machines that we use, these are the machines that IST used. We build them ourselves. They are called the Medusa. They have this funny thing of having 2 bodies for a couple of reasons. And here you see all the hardware and the acoustics for positioning, communication, and so on and so forth. Oh, this one skipped. So another project that was extremely, I think this was the most challenging project I've ever been involved with. And this was coordinated by Giovanni Diveri, and Alessio cooperated on this. Massimo? No, you were not here. Okay, all right. So another project that involves the use of networked systems. It was the WeMust project, and I'm sure Alessio will talk something along these lines, but of course on a different path. So normally when you want to find out what's at the bottom of the sea and underneath, if you want to see what's underneath the seabed, let's say hundreds of meters, sometimes even 1 kilometer or so. So the classical way is to have a big ship with an acoustic source that is extremely powerful in sonifying the area, boom, 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 and this penetrates, refracts, and then this ship is towing an array of hydrophones. It's like, not microphones, they are hydrophones. So these are called the streamers. So you collect all this data, and that's it. Now, if you give this data, so here you see a big operation, extremely costly, with a classical boat or a ship, and then the streamers down there, okay? Some of these streamers in classical operations or commercial operations can be 10 kilometers long, right? So now, what do you do with all of this data? That's the beautiful part. I mean, these are some images I got from a company in Portugal that cooperated with us. And so once you pass the data to a good geophysicist, he or she will be able to interpret this very much as the doctor looks at the echo sound image. So what I'm going to see, to me it's fascinating. After processing the data, you virtually cut these slices underneath the seabed, and you see the geological structures there. So they will be able to find out if there are resources there or something even more interesting, and I'll give you another example. It's fantastic what people can do with this. So the problem is, in order to do this, commercial companies use big boats and the streamers, they can get entangled, so on and so forth. And we were very much interested in doing, this is called geophysical survey, or in our case it's called geotechnical surveying. So over small areas to find out what is down there and underneath. So we came up with the idea collectively of replacing this ship by robots carrying the acoustic sources. And then the very important thing is that the streamers are not pulled or towed by the robots. They are independent, and they consist of a number of robots pulling small streamers. So now you have an antenna, and then the antenna is totally decoupled from the source. So you have a lot of flexibility. You can even adapt the form of the antenna, and you can bring it down to increase the resolution. That's the We Must project. So in order to make this work, it requires, of course, a lot of work. So this is one example of the surface vehicle where you see what we call the sparker that generates the sound. And of course, there was an equivalent, the Italian vehicle that was doing a similar thing. So what is required to make these things work at sea? You need cooperation, network, motion planning, navigation, and control. That's what you need. And I like to show this figure because it underlies many of the things that we are doing at sea. So first of all, you need to plan. So it's cooperative motion planning. So once you start the mission, you need cooperative navigation to find out where you are. And then once you know where you are, and given that you know where you wish to go, you have the cooperative motion control. All of these things have to be in place and working. Now, it's easier said than done. This is what we did together with 2 vehicles at the surface, in fact 3, and then 4 vehicles underwater. 2 of them were Folagers, and the other ones were our Medusas. So you can imagine the symphony that was going on, and one of the difficult things is to communicate and to position yourselves underwater, but we managed to do this with a beautiful consortium that of course included Graaltech. I'm going to skip this one, just to give you a glimpse of the final tests in the water. 133. I have a hard time. 33. It should be around here. So I don't know, I cannot increase the sound. So here you see the vehicles in the water, the beauty. The video footage is taken with a quadrotor. So you see some vehicles at the surface, and then there was a third one, and the vehicles underneath. And this is what happened. I mean, it was a miracle. You see the streamers operating and then collecting the data. This is real data, but of course it's sped up. And you see the vehicles running this sort of line mowing, not so much a line mow, and this is seen from the top. It's beautiful to see when it works, okay? So then you can do an interpretation. There's a commercial side to this, because then we were approached by a company in Holland and the other one in Portugal that said, okay, maybe that's a bit far-fetched. We are in the market, but you want to come up with a relatively simple solution in order to do seismic surveying near shore. So we decided to build this contraption here, where you have a catamaran, which is our catamaran, and the arms are extended, and you have the streamers there, you don't see them. So we did the first commercial survey for Électricité de France in 2019, mapping an underwater geological structure near a nuclear power plant, because they needed to intervene and to set the foundations for further infrastructures. So it was very successful. So we are in the act of transitioning and actually developing a spin-off company to commercialize this in, of course, with a better surface vehicle. This we built in the house. So recently we started what I consider to be a great project, also involving network system that is called Ramones. It's a FET project. Radioactivity monitoring in ocean ecosystems. So the marine environment is significantly undersampled in terms of radioactivity. You need to find out maps of what is going on, detecting sources, either man-made or nature-made. So the question was, can we do it in a radically new and highly innovative way? And so we came up with the Ramones concept, where we have a static lab, radiation instruments, and then we have 2 autonomous underwater gliders and 1 autonomous surface glider. and this is an artist's rendition. And we have to engage these vehicles in talking to each other, sniffing with special sensors and doing what we call adaptive sampling to then find out a map of radioactivity, which is not easy because radioactivity, some forms of radioactivity is carried out and diverted by the currents. So this started in January of this year. So again, we have to do cooperative planning, navigation, and control wave glider, 2 underwater gliders, and the Benthic lab. So the technological challenges, again, you see, it's a recurring theme, navigation, control, and now event-driven adaptive motion planning, because you need to do adaptive sampling, and then you have the assets and they have to communicate. This is being coordinated by Theo Metsimekis from the University of Athens in Greece, so I have very high hopes for this project. I'm very glad. So that's the Ramones project. New soon, I hope. So let's give it a more recent twist, a technical interlude on things that we have been doing since July of this year. Very quickly, 2 things. One of them is based on the PhD thesis of my student, Nguyen Hung, and he's very much interested in cooperative and control of multi-agent systems. And here is one of the problems that he solved, which is when you have 1 or more targets and you want to lead them along certain routes, then in order to find their positions, you can have 1, 2, or more vehicles. And he formulated the problem of, based on range measurements, as Vlad was mentioning, finding out where the target is, run an estimate of the position of the target, and at the same time, move along with the target. That's what we call pursuit. And he did this in a very interesting and clever manner using, and this I have to accentuate, it's a distributed system that involves distributed, event-driven communications and distributed controls. So there's some mathematic paraphernalia that I'm not going to talk about. Here you see the situation where you have 2 vehicles, the initial region of uncertainty, the 2 at the top, and on the fly they decide over a moving horizon how to move to maximize a certain measure of the information. And then in the long run, you see the estimate converging very quickly to the real position of the targets, and they move along with the targets. And we are going to carry out further tests of this actually tomorrow. So experiment preparation. So how do you convert this into practice? 3 Medusa vehicles, and now you have all the code running on board. And I'm going to show you a little bit of how the tests went. I'm about to finish, don't worry too much.
Oh, no, you have time.
Okay, so what you see here, it's quite interesting. Because we all know, I mean, we have known this for so long, that when you have target going on a straight line, the best strategy is for the trackers. For example, it's one possible solution, to go in spirals, and this is the real data. These are the real vehicles. Maybe you can see them very well. This is happening live, and here this is what we are watching from shore. Of course, there are other solutions where you don't have to circle the target, and essentially you have to move along so that the angles between these guys and the target are 90 degrees, but automatically these trackers set the angles and maximize the information available for positioning. We did this at the surface using Wi-Fi and emulating range measurements. Tomorrow, we'll make one of them dive and act as a target and use acoustics to do all of this stuff. This will open the way for a number of missions that I consider to be extremely interesting. So the other thing that we have been playing with, and we have been getting a lot of help from CMRE, and this is joint work with Roberto Petroccia, Luca Morlando, Marin Stepanov, has to do with a fantastic topic that has to do with hybrid acoustic optical underwater communications. Because most people, you know, classically we use acoustic communications. They are very costly. The baud rate is not extremely high. It's very hard for many modems to coexist because you have to go through a protocol for interrogation. So why not combine acoustic communications, long range, low bit rate, with optical, for example. We are not exploiting the other options, short range, high bit rate. Now, what we want to do, and we have done this to some extent, and tomorrow we'll do again an experiment, is to do the formation control using acoustics. Because there's one thing that is extremely important. When you have optical modems, and this is the optical modem that we developed at IST, they have narrow beams in order not to disperse the energy. So if you have the vehicle scattered and you want them to talk over the optical modem, God, you have to synchronize the beams, align the beams. How are you going to align the beams? That's another story. So what we do is, when they are far away, use acoustics. Once they get sufficiently close and close to the formation, if you want to exchange data at high rate, we switch to optical modems. And we are using the algorithms, the software called cognitive communication architecture that decides on the fly when to engage one type of modem or another type of modem. So this is the very last thing I wish to show you. So here we have the boards coming from CMRE, and here you have the Blu-ray optical modem installed on board one of the Medusas, and I'm going to show you a little example, 137, sorry. It's hard to see. So, okay, let me stop a little bit. So, two vehicles. And the image you see there, the dot is the projection of the quadrotor. They are trying to do formation control, going over a path side to side, but they are using acoustics. So the beams are not locked. But when they get into the formation, then you'll see very clear the beams locking, and then you can change your data, like if you want to transfer, there you go. And then you transfer the files very, very fast. I find this fascinating. So, a problem for those of you that want to think about this. Suppose that you want to be more sophisticated and not wait for the vehicles to correctly align themselves. How can you point the modems? So that's where I see a beautiful connection between this and event-driven communications. Because event-driven communications, each vehicle sort of runs an estimate of where it thinks the other vehicles are. So it can do a preview and point the beam there, and the other one does the same. So I'm just leave this flying in the air, which I believe to be very interesting. And now, in order to somehow combat this problem, we are developing what we call an omnidirectional Blu-ray modem with 7 receivers, probably being able to receive from different directions and also measuring the angles of arrival. So it's just a teaser to complete my presentation. Thank you.
Antonio, thank you. Thank you really very much. A lot of things were discussed. We do have some time for questions. We have at least 5 minutes, so I think from the floor.
So,
Which is the land? The grid is land that you can cover
with optics?
with the blue
With
optical.
Oh, okay. As you know, it depends on the transparency of the water. In the Azores, we can go up to 20 meters. 20. But it's a very low power modem, okay? In Lisbon and the river that is so polluted, you can probably go twice the visibility distance, which means sometimes 5 or 6 meters. But the controls and navigation are quite good at this point, and you can safely bring the vehicles to that distance. So, yeah.
And then they consume energy, they are energy consuming.
I don't remember the figure, it's somewhere in here, but then we can talk about that.
With respect to the acoustics.
Oh, yeah. They consume much less. And the price, I mean, building a modem like this one with LEDs and simple receivers, the total cost including the outer shell, marinated, probably 400 euros, which is good. Yeah. So if you want the schematics, we'll give it to you. We want people to
start using them.
start
That's very good. Alessio maybe, or Vladimir? Oh, Vladimir, you had a question? So, go ahead.
Okay, yeah. So Antonio, thank you for the really nice talk. A question about the basically searching for target and being able to do that without the traditional spiraling maneuver.
Yeah.
So the movie that you showed with Wi-Fi now, you had really, ability to move after, let's say some definite time into the direction with the target and stay on the path with the target. Is that the whole point? Because all the ones that are showing the spiral maneuver, as you know, it's energy not friendly, because you have to, exert much more energy than you want. So
Yeah.
basically, it's
Yeah.
prohibitive as far as energy.
Yeah.
So
Well, as you know, for example, the work of Boole, if you have a stationary target and you have many sensors, how should you place them, the sensor placement problem, to maximize a certain measure of information? It's along a circumference with a certain radius. So people thought, as you know, well, if I only have one single one, let me pretend that single one over time is going to act as if it were many. So thus people find this solution. Now, the very interesting thing is that when this solution came out of mathematical formalism, immediately we could see that depending on how you started them, it would either lock with two vehicles, for example. They would either lock into this pattern or behind the target, forming 90 degrees and flying along. So you don't have to go bananas. And the amount of information that you generate is exactly the same. So life is simpler.
great. Yeah.
Okay?
That's very encouraging.
Yeah.
Alessio, no? Okay, I have one small question, Antonio. I found extremely interesting that project where you do the survey with a catamaran, carrying the streamers, if I understand. Yeah, I wanted to ask you, what about the sources? Are you still using two sparkers?
No, just one.
Just one, okay. And it's carried by the boat, by the catamaran?
Yes, exactly as
Okay.
we used for the WeMast.
Okay,
Yes,
okay.
we've done it.
That's very interesting.
Now, if I have some more time, so people may ask, so suppose you have a target, and suppose that the target is a collection of vehicles with streamers. So you think of the center of mass, it's the target. And now you have these vehicles on top that not only position, pursue, but also they have to eliminate the target acoustically is in WeMast. There is an advantage in this case in having these guys go around, as you know, because you hit different cells of the seabed from different angles, and that's when you get good results. So it seems very unnatural, but sometimes it's useful. Yeah?
Sure.
Okay.
Enrico.
So, given all the history you have shown, what do you consider to be the next big challenge in terms of cooperative control and navigation of this kind of application?
Okay, for example, one thing, we have all written these beautiful papers about cooperative control and navigation, and then using the formalism of networks and topologies and connected and all that stuff, where we assume that all these vehicles can talk to each other underwater. I mean, we know that it's not simple. In WeMast, we didn't do it that way. We are going through a route up there. So there's very serious work to be done there if you want to go in this direction. I think going for the hybrid will probably simplify life. I think the most important thing at this point, when we talk about network systems, has to do with adaptive sampling. Given that you want to measure or get a good map of some field, or scalar or vector variable, and given that you have energy constraints, temporal constraints, what's the best strategy for these vehicles to maneuver and acquire data to maximize the information available to build the map. To me, it's one of the most exciting things. And I'm leaving aside problems like autonomy at sea. How do we leave these babies there, not for 1 or 2 days, but maybe weeks? I don't know how to do this at this point. Okay, so many things.
Okay, Antonio, thanks again.
Thank you.
The next speaker is Alessio Turetta. Alessio, if you want to sit here, take my seat. Here, there is the HDMI cable.
Fausto sends his regards. He says he hasn't seen you in a long time.
Huh?
Fausto Ferreira.
Yeah?
He sends his regards.
He's in Shibent today. I spoke with him this morning, he was driving. Yeah.
Lui ha bisogno di...
This one, I guess.
Oh, yeah, yeah.
Thanks. USB-C.
Otherwise,
Now-
you'll be dead.
Yeah, I forgot it at home. I had to go at home. It's 5 minutes from here walking, but yeah,
2 minutes running.
2 minutes running maybe. Okay. Okay. Thank you. Can I remove this while talking? Okay, because otherwise it's complicated. Okay, thank you for having invited us to join this event. That is very nice and interesting. I will start by giving you very brief information about the company. As Giovanni said, I'm a business development manager, so I'm supposed to advertise the company, so I have to tell you a few words. And then I will give you some indication about the application domain I'm considering today and the motivation for R&D. And finally, I will talk about some interesting R&D projects related with seismic surveys with AUVs. Just a brief information about the company. We are based in Genova, here in Italy, and we have been established in 1998, so it's more than 20 years that we survive. It's an engineering R&D, small and medium enterprises, currently with 22 people, but we have 3 open positions, so we are looking for interested people joining us. We do design and realization of mechatronic systems in general, and we have all the competencies in-house to realize robots, and we are focusing on marine applications since almost 20 years. What we do some products. This is one of the example, a hybrid AUV. We do modules for the AUVs. We have surface vehicles supporting the AUV in operation, acting as a gateway buoy. We have some reconfigurable AUV or ROV robots. These are just a few pictures. And we also have some manipulators, electrically driven manipulator that we design and develop for the customer. But in particular, for the purpose of this talk, the thing we do that is interesting is R&D services, because almost 90% of the time of our people is spent in R&D projects, either funded by public funding or more often by private industry. And so we have 3 ways of realizing innovation. Either realizing prototype when the customer arrives with a list of specifications that he has in mind, or we do public funded research project, the third point, which is a more classical one, or the second one, what we call beyond prototyping, that happens whenever the customer comes with an idea that is not yet translated into a set of specification. So we sit together with the customer, we make a plan, we do engineering, we do test, and we continue iterating in this way until we conclude, we reach the goal. Now, this is what we did for these projects that I'm going to discuss with you today. If we talk about seismic, Antonio already introduced the topic. What is a seismic survey? Basically, there is the necessity of characterizing the subsoil surface structure. So there is normally a vessel with a source injecting energy in the water. The energy goes down, penetrates into the sea bottom, and then is reflected and refracted, and is collected by some receivers. The receiver can be, as Antonio showed, attached along streamers that are normally towed by vessel, and a vessel towing the streamers is considered the largest man-made moving object on Earth, because as he said, the length of the streamers can reach more than 10 kilometers, and the wideness is around 1 kilometer. So it's a very huge stuff with a lot of obvious complications in operations related to maneuver, to permission for moving, because when they do survey, they need to go in advance in the area to ask for permission, to pay money to fishermen, not to make them going at sea for the period of the survey, etc., and so on and so forth. There is an alternative strategy which is based on bottom nodes. Bottom nodes are sensors that are deployed and on the bottom, that sit on the bottom and record. The problem with this is that the deployment, if they are done with, normally they are done with ROV, they are put in a kind of structure that is deployed on the bottom, then ROV goes one by one and deploy in the given position, so it's costly. Deployment and recovery. The alternative way that is more recently explored, I don't know if you can appreciate, but there is a rope, it's called nodes on the ropes. The bottom nodes are linked by a rope that is used for deploying and for recovering. Operations are faster in this case because it's easier. The problem is that it's hard to guarantee the proper positioning of each node, especially in deep water application. So, given this limitation, the long-term vision of this research is substituting the streamers or the set of bottom nodes with a fleet of small, very low cost, this is a key factor, AUVs, each one capable of carrying a seismic payload, so sensor and recorder. Now, the first project we have been working in, it's 10 years ago, I realize now, and it was called SpiceRec, the phase 1. And just to give you an idea of how things happen sometimes in our kind of R&D projects, the customer came to us with this video. I hope I can send it there, yes. And said, we have in mind this. We would like, I don't see here. We would like to, we are envisioning this kind of scenario where a set of AUVs are in the order of thousands, because thousands is the order of magnitude of vehicles along the streamers, because they are spaced some tens of meters, but there are 10 kilometers, so there are a lot of vehicles. We want them to be deployed somehow in a very fast way. They need to be able to navigate to their target point, to reach the assigned point, land with a certain accuracy, stay there for a while. Then, once all of them are deployed, the real survey, first, the assessment of the position, because it's important for what Antonio was mentioning before, the reconstruction after in post-processing. They need to know where each node was when it recorded data. Then there are the shooting vessel injecting energy. The energy is recorded. And then after a while of recording, every vehicle is receiving signal for, at that time was IPAP. IPAP is a brand of, is a commercial product, but because at that time was considered a good one. Every vehicle is receive wake up signal, comes back to the ship, and then, okay, kind of fiction, data are downloaded immediately, battery recharged immediately, but this was just for okay, showing the concept. But this was what we have been asked by our customer, and he said, I want to do this. Okay, as you can imagine, it's not easy to approach this kind of big vision. So we started together with them to approach the problem with a sort of proof of concept. The first thing we did, we considered an available vehicle of our store. At that time was called Folaga, now is retired, let's say. And the idea was showing the capability of an AUV to land accurately in a spot, and then once receiving the acoustic signal, to wake up and to reach a recovery basket. This was the basic idea. So we did some modification to our vehicle, we did some tests, and then we made some final experiment with landing, and where the AUV is localized, the AUV was mounting the IPAP device at that time, was localized, was receiving correction to be steered and to land at that time. CGG Veritas was our customer at that time, and the vehicle was capable to land close to the border of this circle that was 1.5 meter range, so well within the 5 meter range specification. The similar results was for entering in the basket. That was done by equipping the basket, the recovery basket, with some hydrophones that were pinging. There were 3 hydrophones pinging at different times, and based on the difference of time of arrival, the AUV was capable to understand its own position and to correct by lateral and vertical translation, thanks to the mobility of the vehicle, in order to correct and to be positioned to the center of the basket. The AUV, while I'm talking, is moving. You have seen at the beginning emerging here, and now you will see shortly reaching the basket that is below. It's not so exciting video, but just to show you that at the end it enters into the basket. It's going slow also because it's keep on correcting its own position based on the received acoustic signal from the transponder. Okay, this was just to show. After that, okay, we were happy. We centered the proof of concept. It was March 2012. I put the month for a reason, because we started the real phase 1 in May, and the goal was making 20 vehicles to be ready in 2014, 2 years, but while keeping in mind phase 2 and phase 3. Phase 2 and phase 3 were with a huge number of vehicles. So we had 3 main challenges to face: target reaching, how to guarantee the sufficient position, sea bottom holding, and seismic coupling, which are related to each other. As the goal is staying on the bottom and record data, they need to have a good coupling with the sea bottom in order for the sensor to acquire good data. And this is not trivial, because for having a good coupling, the vehicle has to be negatively buoyant. And as you all know, normally AUV are slightly positive for safety, or neutral in the better condition. That vehicle had to be negative, at least while recording. And okay, we started with the engineering phase. The first decision was the shape. This is just to motivate that at the end we had to choose for a Toblerone shaped AUV for motivation that are outside our control, not for engineering reason, because the cylindrical is well known to be better. And so we started with the first concept that was very simple, and in July of the same year, we started in May. In July, we had the first mock-up, the first prototype, just to please our customer, to show that we were agile enough to accomplish different needs. So we started with test. Okay, these are very basic motion, not so interesting to see, with the vehicle in a pool at the beginning. Then we went to a lake to start better test. And in parallel, we started testing coupling by going into a river where there was some current. Then we sit with the customer and we analyze the different lessons learned. We had to shape, to improve the hydrodynamic capability for better target reaching, and we started with new tails, new noses. We tested different shape of nose and tails, and we made a lot of other tests at sea for navigation, while improving the performance in navigation that is fundamental for then guaranteeing a good target reaching. For sea bottom holding, we introduced the concept, actually the idea was from our customer, the magic carpet, what he called. The idea is just having a surface with some holes, little holes like the cup of a shower, where water can be injected, and this, the little hole generate a flow that allow to, what we say is not properly correct, fluidify the sand in order to allow the vehicle to make the soil, let's say, less stiff and to penetrate a little. I will show you a video later. Then, of course, there was also the need of inventing a sensor for understanding that the boring was successful, but I will show you. And then the other point was the positioning of the sensor, how to couple this to the bottom of the vehicle. And we realized two different releases of the vehicle that were used for doing seismic tests. Then we spent other time, I want to make the story short, and we finalized with these two vehicles, Eco version 1 and version 2, and we collected very good results with negative buoyancy, which is not, at that time at least, was not so common, navigating with a -2 kilogram buoyancy at 2.5 knots. The speed was somehow necessary to face with this negative buoyancy, because like an airplane, and also exploiting the flush surface for having an increasing lift to sustain the vehicle. So these are some graphs showing the good performance of the vehicle in navigation, but I want to show you some videos with a mission that was recorded in Sardinia. Sardinia is like Azores in terms of visibility, is the Italian best site for visibility. We went there just to take this video, and this is the vehicle navigating with 2 kilograms of weight. You will see now that once it stopped the motor, it just goes down by gravity, by lifting a little of sand, and then it is starting to use the magic carpet. So you see this, I don't know how to, a good wording in English, but the idea is making the surface level more easy to be penetrated. And there was an alternate, it was alternating this activation of magic carpet with the vertical thruster pushing down. So it was making this for a few seconds, then pushing, then again, and then pushing. And after a while, the white thing you see is the burial sensor that we developed. It's a sensor that understands when it is covered by sands. So after a while, it is able to be few millimeters inside the sand, but those few millimeters were considered enough to guarantee a better coupling and, let's say, facing a little with the current. Of course, not with strong bottom current, but it was enough. Then, once the acoustic signal was received, you see the acoustic transducer on the top, was received, the vehicle was able to take off and to go back to surface. This was a vertical takeoff. Then, of course, before reaching the desired speed, it was going down, because as I told you, it needs a certain speed to sustain its weight. But after the speed is reached, it can move. Okay, and this is one. The second one is very similar. I could even skip it for sake of time. It's a few months later. The only difference was in terms of takeoff. I don't know if I can go faster. No, I'm not able. Anyway, the takeoff was done by having the nose up first and then taking off like a airplane somehow. Okay, but I can skip it. I don't want to waste time because I have a lot of things to tell you. The second important project was Musafir, phase 1. And here the address said, while the first one was for bottom nodes, this one was for streamers, for finding a solution to streamers, based, as we said, on a fleet of small AUVs. So at that time, phase 1 was launched, and the idea was showing that the operational model based on robots was achievable. So the idea was just having a reduced scale demonstrator in water, and the idea was having 16 AUVs in water for some days, recording and checking the quality of data acquired. So we started again with our available vehicle for a number of reasonable motivation, low cost, etc., etc. And the target operative scenario was with a C2 vessel and 16 AUVs in the water, 6 spare on the deck, in order to be substituted in case of failure and to not stop operation. And we did it for 30 days. And there was not a real cooperation, as in the case of WeMust. It was even less than in the case of WeMust, because the control was centralized. There was a C2 vessel where there was a USB-L antenna localizing all the vehicles, then computing on board the C2 vessel the correction for each of them, and then sending through a modem the correction. So it was, from the control point of view, I know that Antonio Pino and the others are saying this is a very easy job. It's true, I confess, but there were a lot of other. It was working, it was enough, and the goal was just showing, as I said. But there were a lot of things to do. First of all, making 22 vehicles in 8 months, because it was not easy for us at that time. We had to prepare the seismic payload by having good, in this case the payload, there was not the problem of coupling because the vehicle was in the water, but still it had to be able to record and to acoustically be guided by the C2 vessel. And more software development, because despite from the control point of view it's easy, from the C2 point of view and the control and all the operation was not, there was some strong activity to be performed. In terms also of a graphical user interface for understanding what's going on underwater. Because in a mission taking 10 hours per day, you need to know what is going on underwater, where the vehicles are, etc. And then a lot of tests at sea with launch that is easy, is very intuitive, but okay, I don't have, unfortunately, the video. Recovery is more complicated because by towing is not easy. So we had to invent a way to, with a winch that was hooked to the nose of the vehicle by an operator close by, and that allowed to, let's say, recover a batch of vehicles with these ropes. I don't have, unfortunately, all these videos. Then, once we did the vehicle, we mobilized, and we finally were able to go there. And this what happened every day. Deployment at dawn, then swarm supervision for 10 hours. That at the beginning was exciting, because when we saw things working, we were happy. But then after a while, it was boring, because you were looking at the screen all day and was not so enjoying. Then recovery, that took a lot of time every day, between 45 and 1 hour and a half, depending on the sea state. So it's a huge energy again. Then washing the vehicle, charging the batteries, and downloading the seismic data every day. And this was continuously done for 30 days. So it was also intense experience in terms of test. Then, I will not talk about WeMust, I just put here a reference to some videos that are available on YouTube for those that are interested and are looking at this. You can check and see some videos. And I removed the slides while I was sitting there. Then Space Rec Phase 1 continued after, because in 2014 it was stopped with ECO, the one in Sardinia, because of management change in our customer. As I told you, the vehicle were to be produced in 20 units to show the capability of landing, 20 units landing in a desired position, and then to move forward with Phase 2. The new management went to a different company for R&D, but they were not good enough, let's say, to provide something that was good for them. So they came back to us. The management changed in our customer, changed again. Our previous contact were put in charge of the project again. So they came to us and said, we have to save the project. We need to show that we can make 20 vehicles land in a desired position with a given precision and stay there for a while. How can we do? We said, the only vehicle, 20, that we have available are the one used for Musafir. So the idea was modifying them to make them heavier and to make them more stable by adding these wings that you can see that were able to trap some sands in order to make the vehicle stable. So again, we had to work in a rush. We start doing testing in La Spezia. We start testing the deployment in a line of the 20 vehicles, and we modified the C2, and finally we went to the Arabic Sea for doing the test for our customers, and we were able to save the project, let's say, to show that the 20 were able to land in their assigned target position with a given precision during a real survey. So there was this is the air gun that is going to be deployed and was shooting for some days. It took, if I right remember, 3 or 4 days shooting. And these are the lines that were similar to the one of the WeMust project that were followed by the ship for injecting energy into the water. After this, we were engaged for Phase 2. Our customer, was approved, and the Phase 2 of the project could start 2017. And as you remember, we stopped with Eco vehicle, so we went on with Foxtrot because we followed the name of a NATO alphabet. So we end up with this Foxtrot vehicle that was supposed to be manufactured in hundreds of units. So what we did was we modified completely, started from scratch, the software architecture, because managing 200 vehicles is a different story than 16 or 20. And we started doing the vehicles and spending a lot of time testing them at sea. That is complicated when you have a big number, also from logistic reason. We had to work with a new recovery device because it was not acceptable having an operator hooking the vehicle on surface, etc. So we had this recovery basket that was a kind of basket where the AUV are, after the mission, are driven acoustically. The red dot here are pingers, are driven acoustically there to be recovered. And then we manufacture the vehicle. So these are the 220, because 200 in water plus 20 spare, that we realized this is our office, our premises. And then we moved to the test in 2020. This is the container where all the vehicles were installed. I had to remove some pictures because of confidentiality, and I cannot show you video, but I can just show, hopefully, without any infringement of But okay, I hope it's okay. These are pictures taken by our mobile phone there, so I hope there's no problem. And this is the test vessel that we used for this final test, where the launch was obviously done with a ramp, as in the other story. And these are some of them intentionally put close enough for this picture. Of course, for a real seismic, they need to be 50 or 100 meters far each other. These were put intentionally for the picture. And this is the recovery basket that was used for recovering them, where you see the number is around 20, the number of vehicles that can be hosted in a way that cannot be more, because when they are out of the water, the weight of, you cannot guarantee that they are well positioned inside, so you can have more than once on top of the other, so it's risky for the vehicle themselves. And that's it for this project. I cannot show you the videos. And just I want to conclude with an ongoing project that is Musafir, the one in water column phase 2, that also Musafir was okay in terms of showing the good capability of the vehicle, so it was promoted to phase 2, where the idea is moving from 16 to 100 vehicle in perspective. And in this case, we had to change significantly the way of controlling. Of course, it cannot be done in a centralized way. And we adopted an approach much similar to the one in WIMAST, where there are some, what in WIMAST were called anchor nodes on surface, equipped with GPS, that are sending acoustic messages that are allowing a huge number in perspective of vehicle to self-guide themselves, self-localize themselves, and follow the desired trajectory. I think I'm long, so I stop here.
No, it's perfect. 30 minutes right now.
But okay, but I have to leave time for questions. Sorry. That's it.
So thank you, Alessio. Really, thank you very much. This was extremely interesting, at least for me. I have more than one question, but I would like to give the floor first chance. Yes, please.
Sure. Okay, the control strategy was with the USBL in this case as well. With every vehicle was localized. They were deployed in batches, and they were localized with the USBL. That was in any case mandatory. The problem is that they need in any case because USBL transponder mounted on the AUV is costly, it's expensive. It's probably one of the most expensive part of the vehicle. The problem is that so far they cannot abandon this because they need to localize the vehicles once they are on the sea bottom. Because in any case, as I told, there is a range of accuracy of around the target which is acceptable. But even if it is inside the range, they need to know where it is in order to then use this information in post-processing for analyzing the data. So once this device is on board, it's worth using it also for navigation and localization.
Sure.
Yeah. Oh. But it's not, if I may infer it's not good for a scalable solution, because you cannot have thousands based on USBL. You can only if you deploy them in a sequence. It is true that this solution is not acceptable for the Musafir project, the one on the water column, where navigation is 99% of the time. It is acceptable for the node on the bottom, where deployment and navigation is limited with respect to recording. So you can accept also thousands of vehicles to deploy one after the other, or a batch after the other. Despite it takes more, is not the big issue, because then once they need to navigate a few hundred of meters, then land and then stay there for days. So it's acceptable to have this. From the control point of view, it's simpler, the spice rack problem, the one on sea bottom, than the Musafir or WIMAS, where they have to navigate for a lot of time. Yeah.
Antonio.
Thank you. Thank you.
Very nice. Now, having said that, there are two questions. Remember when we were working together in WIMAS, the quality control, we always broadcast about this. How is this problem being approached?
Yeah, okay. For the nodes on the bottom is not like now, is not a problem that needs to be solved real time, because even now for the nodes on the bottom there is no way to have quality control with the current means. So in that case, in that scenario, it is not a problem on the table. For the other, let's say Musafir phase 2 or phase 3, if we will be lucky to have it, it is a problem in the sense that they want to have a kind of feedback information, but it is considered acceptable to have some feedback information seldom, let's say every quarter of hour. So now the specification for the hundreds of vehicles in the water column, is having a feedback from each of them every quarter of hours. Okay. And in that feedback, there is the status of the vehicle, some information, and also some very brief information about the quality of data.
The other problem is related to what, optimal sensor placement to measure things and the energy constraints, temporal constraints. Suppose you guys want to do a survey of a certain portion of the bottom of the sea that geologically is not very interesting over a huge area. Why go through the effort? Is there any way, based on the data acquired, to do an extension of a prediction of what lays ahead, and then decide on the type of nodes, how many?
Yeah, well, this is more a question for geophysical and but I can tell you that what we have seen so far with our customers, we have worked with two different companies, big companies in terms of geophysical surveys, is that they are not so. Who can see this one?
Everybody.
Everyone.
Everybody.
Okay,
Yes.
Sorry if I say this. They are not so open-minded in terms of embracing possibly new operational model. They can accept a different piece of equipment, but operation, because when you give them a new sensor, is something that it's a tool. They can accept a new tool. If you start talking about different operational model, different post-processing technique, you enter in their domain, and they are more conservative.
Conservative.
Yeah,
That's
conservative.
conservative.
Better conservative than
Yeah.
open-minded. Okay.
Yeah, I'll just take advantage that I was talking already for a small, but to me, deep question. So I remember we discussed this a time ago, but I'm still not 100% convinced, or I haven't understood, probably more simply. You showed the traditional way of acquiring this data with streamers, right?
Yep.
And then you pass to your approach with the bottom nodes or these large numbers of AUVs. I can't not still be completely convinced that it pays off in terms of the number of hydrophones that you are using. I mean, with the streamers, if you want to double the resolution, you just add one hydrophone every, in between two.
Yeah.
But if you had to do the same with the vehicles, you would have to double the number of vehicles, which is, does it really pay off? I mean,
the target price, the target cost of a UV is in the order of 5,000 euro per unit. Target cost.
Okay.
In perspective,
Yeah, but the hydrophone costs.
But putting an additional hydrophone every two in a streamer, it's going to cost more. I mean,
You think it
yeah,
is?
because you need also to do it. And there are some maintenance costs which are not trivial. There are barnacles that are attaching to streamers that needs to be periodically cleaned. I mean, in terms of operation, this is probably the only thing that is considered by everyone in the domain a clear advantage in perspective. There are some big issues to be faced, because if you, especially for the scenario kind of Musafir, like we must, if you think about thousands of vehicles in water, they need to be periodically recovered, recharged, and redeployed.
Sure.
So you need to have a way for recovery, a mechanism for recovering batches of hundreds per hour or something like that. That is
Challenging.
It's challenging. Let's say challenging. Okay, this is, in my view, the main challenge to be addressed, because the AUV, okay, the AUV or the control and navigation, etc., is something that can be done. We did it, and whoever here did, but finding a way, especially in bad sea state condition, for recovering a big number of vehicles periodically, etc., can be a challenge.
Yeah, so we are a little bit late, but please. No, go ahead.
Maybe it is a problem now, but when you have to manage so many vehicles, that it seems to me they work very close. Is there any danger, and in any case, what you think that to do for recovery? I imagine some possible catastrophic effect when you have collision between 2, then 3, then 4, and so on. You know, when you have many people staying close and doing something very dangerous can happen. And I imagine that with 200 vehicles or more, there will be some catastrophic effect when you perform your trial. Is it true?
Well, I can tell you that we tried several times to let's say for fun. We tried several times for fun to make two vehicles to touch each other. We never succeed. we could never able to make one going. For sure, if we don't do intentionally, it will happen. I agree with you. No, well. Some kind of catastrophic event like this that you start with 2, I don't see really, because for the vehicle deployed on sea bottom, they need to go few hundreds of meters each and then stay there. The other one navigating information, in principle, everyone doesn't know that there are the others, except for. Okay.
Well, maybe it's not for now. Maybe it will never happen.
No, not so far. Not so far.
Okay, I don't know if there are maybe just one last short question. Yeah, go ahead. Vladi, sorry. So two questions.
If
One
we may.
from the floor and then Vladi.
You said that one of the difficulties is retrieving them, right, the AOV. You're using a basket to retrieve them, and you risk them overlapping and damaging each other. Why is it not feasible to use a conveyor system?
Like the one in the video, that was kind of fiction, science fiction. I mean, going down. No, it's not. At least it's not simple. It's not doable, especially with the sea state. It's not easy.
And why use a basket and not like a shell system where they can't overlap?
Because it's simpler in terms of control. You just need to go there to switch off motor, and then you go down for gravity because it's heavy. And while positioning in a shelf is require more accuracy, it's more complicated.
Vladimir, please.
Okay, so my question, and I think it's also a suggestion, but I think will inspire maybe some discussion later when we have time. But I think it connects all the three presentations and also connects all the questions that were asked, that people ask you. So it connects the question that Antonio asked about, can you do some deployment and get some idea and not deploy thousands of them, So also same thing for, I guess, Giovanni's where it's, is it cost effective to do it? I also don't know, but assuming it's cost effective because someone decided to say multiple vehicles, not vehicles towing, because problem with vehicles towing, it's all over the... So having worked with a system where we had to deploy something and had it go to a specific location on the bottom also connects with the, basically business of a traffic that Pino asked, and also about the cage. So is there a possibility to deploy cages first with many of them so they travel only short distances on the bottom versus traveling from the boat while the boat is moving, and then releasing them from the cage? Again, shelf, cage, engineering, different thing. But releasing them, several of them, to get an idea about the bottom, and then possibly deploying all of them. Because I think possibility of them returning to the cage in the short area, a small area, it's easier, perhaps. And then also that cage to be recovered all at once by the boat. It can be even the size of a container, Connex box container, shipping containers. They've done it. Like you can have some winch system to take it out. But again, you can just comment and we'll have maybe some discussion. Also for acoustic positioning, where my presentation and everything, when you have things locally, you can do things. But when you are far away with the ship to do the geo-referencing survey, it's more difficult. But with the small local acoustic system and a buoy on top that speaks with a RF with the ship, I think you can do the precise positioning.
Okay, many points. Well, the cost effectiveness is based on analysis of the cost of the we have to. It seems the same business, but there are two different domains. The one on the bottom nodes and the one on the streamers. I can tell you that, as far as I know, the surveys with streamers are less and less performant nowadays because they are extremely costly, and also because they are going to look for oil, especially in deeper and deeper region where, of course, having a receiver on surface is not good enough. So the streamers are going to die, probably. Now, the idea of having, instead of the streamer, the fleet of AUVs navigating in the water, allow you to make them going down, possibly down, and closer to the sea bottom or whatever. And deploying them with a cage can be done. We did it. I didn't put in the picture. We did it for the 20 that we went there for saving the project. We deployed with a cage. We made a cage opening on the bottom, and then they were going down. This makes sense and as an improvement if you are in deep water. But has some complication because you need to deploy this cage, etc. Going down for the AUV is not so complicated because they are heavy. They can even, once they go down with a ramp from the ship moving, despite the sea is not a real problem, they can be even switch off until they reach a certain depth and then start going where they need. Because luckily, this is the only advantage of being negatively buoyant, that you can go a lot down without even propulsion if you need. Recovering them in the basket, why the basket is because it's actually they are doing the same job for reaching the target and coming back. They are doing the same kind of motion. They are landing inside, they are reaching a point and then they are landing inside the basket. The number of them that can be recovered is difficult to say. I mean, we said in this one they were 20. In the Musafir cannot be 20 because you need more and more. So there are margin of improvement. The other point that you mentioned, the one deploying a little understanding. In oil and gas, when they do a survey, before doing a survey, they pay for a permission of months of exploration of the area, and it's not they are exploring somehow the bottom. Before doing the survey, they do some bathymetric inspection. They know perfectly how is the bathymetry. Interesting or not, from the acoustic point of view, from the geophysical point of view, you know only after you inject energy with the source vessel that cost 100,000 euros per day approximately, and that is used only when you have deployed all of them. You inject energy, you record, you collect, you download data, you do post-processing that takes a while, but while doing this post-processing, they prefer to move and to deploy in a region ahead. It's not that the AUV has the capability of acquiring data that are good enough to understand if the site is good. Sure. It's a complicated process involving the source, involving the post-processing.
And
it takes
also
time.
Involving all the others as well. It's not involving all the others. Yes. It's not local. It's
not local.
Yeah,
it's not local. You can understand something once you combine the data.
Exactly.
Of a matrix of huge number of AUVs. After shoots done in, as he said, from different angles in order to excite, to inject energy in different and to have view. They say illuminating the sea bottom from different angles, having more beams on the same spot. So,
okay. So sorry, I don't want to be the party closer, but we are a little bit short on time. So I would actually stop here for this talk. Sure. Alessio, thanks again.
Yeah, you're welcome.
I would suggest to have 10 minutes break, not rather than 15, maybe. Only 10 minutes, and then we have the last two presentations. Okay.
Okay, thanks.
Thanks. Quindi alle 50. Our short break, we are starting again. As we saw in the schedule at the beginning, in this session we will have two presentations, one from Massimo Caccia regarding their work at the CNR, and then the following will be from my side about ISME. So, Massimo, please, the floor is yours.
Thank you, Giovanni. I'm Massimo Caccia. I'm a researcher at the National Research Council, now in the Institute of Marine Engineering. And my presentation today will focus on a short introduction of this institute that is just a bit new inside CNR. It is only 3 years old. And then we will focus on, in particular, what we do in marine robotics, focusing on the vehicle that we developed during last 25 years, and then on new ideas related to vehicle concept that we are developing now, and the European projects we are involved. And so, which is the background of the Institute of Marine Engineering? It was founded to put together all the competencies in engineering that are inside the Italian National Research Council. And in particular, we have 3 main headquarters. The central headquarters is in Rome, where there are competencies regarding ship architecture, hydrodynamics, and so on, that were centered in the Italian towing tank, the previous research institution, INSIAN, that became about 10 years ago an institute of the CNR. And then there was another institute of CNR, more IDASC, more focused on underwater on acoustics. Then we have the part in Genova that came from the Institute of Studies on Intelligent Systems for Automation that I was directing at that time, and was previously the Institute of Ship Automation here in Genova, and we have more competencies in automation, optimization, control, and robotics. And then there are our colleagues who were in our same institute, ISIA, and before a center of studies on power systems. They are in Palermo, and they are more focused for, as far as research is concerned, on electrical power system, conversion systems, and so on, but the applications of their research are basically all on board ships or in coastal areas. So, 3 years ago in CNR, we made this new institute, and that focuses its research interest on all the machines that are at sea, so transport and logistics, smart grids, also in the harbor and in the coastal areas, renewables from sea, ships, of course, marine drones, underwater and surface and aerial, offshore platforms and submarines. And which is the vision of the Institute? We know that there is a key keyword that is sustainability. And so we need to develop technology that allows to develop all these systems being sustainable from environmental, social, and economic point of view. So when we face the development of the technology, we need to keep in mind these 3 pillars. And a possible technological solution to go in this direction is to work on autonomous systems. But for doing that, we have to face many research and innovation challenges in different disciplines that are, on one side, from more in ICT, robotics, machine learning, in some way energy management, because it is more related to grids of energy and so on, and other on more traditional aspects related to the world of naval architecture and marine systems as hydrodynamics, hydroacoustics, and hydroelasticity. And as I mentioned before, the guideline of our research are autonomous systems and bio-inspired systems. Then, going to see something about the infrastructures that are available inside our institute. In Rome, we have basically all the infrastructures of the Italian towing tank, with Umberto Pugliese towing tank and Emilio Castagneto seakeeping tank. And this building is 450 meters long, and in the seakeeping tank, it is possible to generate waves until half a meter of height and 10 meters of length. And the speed of the carriage are about 10 meters per second, and we have something similar also in the conventional towing tank. We have also other infrastructures, such as the depressurized circulating water channel. That is what you see there on the top left is basically a building of 4 floors, and you have the possibility of circulating the water with the water open on the top, and you can test different models, also small models in scale of infrastructure for energy production at sea and so on. And also we have, as you see in the bottom right, movie that we saw before, but maybe going back and forward, we can see it again. We have also the cavitation tunnel of the Italian Navy. This is more traditional, but in any case, not so small. Then we had also different, in Genova, the research infrastructure is basically made by a fleet of unmanned marine vehicles. And we have a long story, as I said before. We're in the second half of the 90s, we developed the Romeo ROV that we used in different campaigns. And we see, for instance, in 97 in Antarctica, in 2000 in European project Aramis to study the thermal vents in Melos Island. And then in 2002, we used it for internet-based operation, both in Antarctica and in Arctic. And then we had in 2003-05 this concept of Antarctic benthic shuttle, so the vehicle released a benthic chamber on the seabed and then recovered it using acoustic beacons one day after. And in 2003 and 2004, we were the first to use an unmanned surface vehicle in Antarctica to collect the surface microlayer of the sea in order to study. At that time, there were some pioneer studies about the exchanges at the interface between water and atmosphere for starting to understand what was going on in global climate change. We developed also vehicles for monitoring of also of ships. In this case, this is a robot climbing with magnetic tracks, and then a small semi-submersible vehicle to recover emergency towing systems in a cooperative way. And we made this project about 10 years ago, exploiting some of the concepts about robot cooperation that Antonio mentioned before. And then we use that prototype vehicle for starting to monitor ice-water interface in the Arctic, and it was the first time that someone collected sample of water just below the wall of tidal glaciers that are 50, 80 meters, and so it is not possible to go by man because it's too dangerous. We developed also, in the meantime, Europe ROV AUV, but there was a kind of version, a smaller version of Romeo, and we exploited it also for gas emission monitoring in Scoglio d'Africa with the Italian Navy a couple of years ago, just before the COVID. Then with the Proteus ROV AUV USSV, we have, as you see in this short graphics movie, the possibility of changing the structure of the, no, okay. Ooh, no, I can manage it. Yeah, because this is reconfigurable vehicle. You have an ROV, but if you mount batteries on the bottom and the acoustic beacon on the top, you have an AUV. And then if you add buoyancy on the top and the GPS and Wi-Fi, you have a semi-submersible vehicle. And in 2017, we used it combined with aerial drones to study all the column from the surface to the air column in the proximity of tidal glaciers in Svalbard Island, close to the Dirigibility Italia station managed by CNR. In that case, we tried to see what happens if we use more vehicles, different vehicles, but for a small surface vessel, it is not a good solution. So 1 year later, we went there with only one vehicle and equipped with 2 winches for deploying and recovering underwater and air sensors. In 2018, we developed also an underwater arm and mounted it on Proteus to collect bryozoa in Antarctica, and all these bryozoa were then planted again in some gauges, and they survived. Here we have some experiments on learning by imitation and other shallow water operations with SWAMP. That is the last vehicle that we developed, and it is designed for ultra shallow water operations with pump jet propulsion, all made by foam and other innovative mechanical and naval solutions. And no? And we're developing our vehicles. During last years, we tried to have a vehicle smaller in size, lighter, with a reduced cost. And on the other end, we tried to increase vehicle modularity and portability. So we had Europe, that is, okay, a lighter ROV, but not so modular. And then we moved to Proteus vehicle that you already saw in different configurations, from underwater and semi-submersible vehicle, and the Swamp catamaran designed completely modular on each hull. Each hull is fully equipped with all the devices for navigation and control, and also we are going to mount also communications. There are already batteries, so each hull can work also as a separate robot. And this is the idea of having modular and distributed robots. As I showed before, we have the concept of ROV, AUV, ASSV, and the USV system based on the Proteus block, because when you have 2 semi-submersible vehicles, you can join them with a frame and you obtain a catamaran. The concept of the Swamp ASV is to have 2 separate hulls that can be connected by rigid, soft, or pure communication links. And all these vehicles are used in a number of European projects and with different applications, maybe in harbor, marinas, coastal areas, and laguna. And we have also a clear capitalization plan of these vehicles during the project. So we have an Interreg Maritime Italy-France matrac, where we use the Proteus vehicle, IUV, with a small buoy equipped with a winch to be kept in shallow water as in harbor, so maximum 12, 14 meters, on the vertical of the vehicle, so we can avoid to use expensive acoustic systems for localizing and the vehicle and communicating with it, but only simple GPS and Wi-Fi connected to the surface buoy. This vehicle and Swamp AUV are used in the Blue Roses project, where and then exploited also. The results will be are being exploited in the Interreg Italy-Croatia project, where we are going to build 2 new prototypes of swamp that will be used also in an H2020 project milestone. In particular, in Matrac, we had this, it is a cooperation between CNR, INM, Institute of Mathematics, Department of the University of Genova of Geology, and the IFREMER. And the goal is this cross-border definition of innovative shared protocols and procedures for monitoring marine waters import based basically on robotics and adaptive techniques. And as I said before, we had the development of this innovative buoy used in cooperation. It is completely passive except for the winch, used in cooperation with the vehicle, and we had also a special tools led on the vehicle carrying the Matrac payload. Then, in Blue Roses, we have a different partnership. Antonio is a research group in IST, is a partner. We have also OptionsNet, Omniver, and Navigo as partners. We have different objects. From the point of view of technologies, the object is to develop a prototype middleware architecture and tools, basically for marine IoT, and different innovative services as guaranteeing remote access to naturalistic and/or cultural underwater sites, remote seawaters and seabed monitoring inside marinas, basically by your own app on mobile, and then studies for monitoring yacht hulls for security and support to refit and dismantling. We are trying to understand how we can develop new services and tools for integrating robots in innovative leisure boats, especially very expensive yachts. And then we have, of course, common dissemination and communication objectives to increase public awareness. And we see here a basic sketch of Blue Rose's concept and architecture, and the 2 pilots. We have one for tourism in Algarve and one for water and seabed monitoring marina in Viareggio. In Innovamare, it is an Interreg Italy-Croatia project where it is foreseen to develop a cross-border DIH on marine technology with a node in Venice in the headquarters of the Institute of Marine Science of CNR. We are going to develop 2 swamp ASVs with their kits and sensors. And from the robotic point of view, an interesting kit is to develop a kind of surface effect ship. This means to put a couple of skirts on swamp, a air fan on the top, and in that way we have a SES. We will transform it in a SES vehicle in order to have faster motion from one point to another, where, for instance, to deploy a multi-parametric gauge with a winch or so on. And also, as a kind of prosecution of this project, we have Maelstrom, where the robotic systems will be developed for monitoring and collection of plastic garbage in Venice lagoon and channels. And in this case, we plan to have 2 different use of swamp. One is swamp equipped with a multi-beam echo sounder to detect garbage on the bottom of the channels, and the other one is to develop a mini ROV to be integrated with swamp ASV, with a winch also, and to operate all this multi-vehicle system connected by cable all together. So this was a very fast, I hope fast enough, presentation of something of what we are doing. And so I don't know, Giovanni, if we want to have questions at the end for both of us, or now, as you prefer.
We can have both. So
yeah.
We have now 1 minute and a half, 2 minutes for questions if there are any. Otherwise, we can have a short final roundtable discussion after the last presentation. Okay, so maybe we can postpone the discussion later.
So now I have to introduce Professor Giovanni Indiveri, who and I want to thank him also for all his effort in organizing this day and this very interesting workshop. And Giovanni, I know him from his beginning, because he had his PhD with our group and Professor Casalino, and now he's the director of ISME and can present you what's going on in research institutions in marine robotics in the universities here in Italy. So please, Giovanni.
Thank you, Massimo. So I don't know if we can switch to my other screen. Oh, there it is. Thank you very much. So Massimo, thank you for the kind presentation. You made me feel old, actually, because we as he mentioned, we know each other since very long. And I started studying in this institute, ISME, and now I'm the director, which makes me feel a little bit strange. But anyway, ISME stands for Integrated Systems for the Marine Environment. This, as you will see in a while, is a inter-university center. And I will tell you in detail what this means, but in particular, the legal headquarters are here in Genova, and in particular, they are hosted by the Dibris department of the university, which is the department working in bioengineering, robotics, and system engineering. As I mentioned at the beginning, I am teaching control systems. And this is the list of the universities that actually belong to the center. So an inter-university center is basically a network of universities, and in particular the ones that you see listed here, that collaborate, sharing, let's say, not only the infrastructures they have, but most of all the brain power, let's say, of people. So the labs located in these nodes, we usually call them ISME nodes, are mostly coming from control engineering, but not only. We actually cover a large list of topics and competences in ocean engineering in general. Of course, robotics is perhaps the most important aspect, but it's not limited to that. We cover communication systems, we cover networking for underwater IoT, AI and machine learning methods, and also equipment, let's say, design and analysis. As I was mentioning, most of our labs are led by colleagues working in controls, but we also have, for instance, in Florence, the node of Florence is led by a colleague, Benedetto Allotta, who is more into mechanical design, mechatronics. So he has a background, controls background, but he is also active, he and his lab are active in mechanical design. The node in Rome, for instance, has a specific competence in computer networking, and they work a lot on Internet of Things and underwater communications. In Pisa, there is a specific competence in acoustic communication and networking, signal processing, on top of controls. And so forth. Just to mention that each node has its own specific competence. Basically, by now we are 9 universities, the ones I listed earlier, with a number of structural researchers that you can see in this lab. The institute was established, the center was established in 1999, so we grew quite a lot since then. It started with a bilateral agreement between Pisa and Genova. Of course, Pino Casalino, that is here, was one of the founders. And the other colleague who contributed a lot, the person in Pisa, is Andrea Caiti, who was actually the director up to last year when I was taking his place. One of the important things to mention about ISME is that we have a very, by now, solid cooperation with the Italian Navy, and in particular with a lab of the Navy that is called CSSN, Centro di Supporto Sperimentazione Navale. I'm sorry, I don't know the English for that. And with them, they are located in La Spezia. And several years ago, I think it was like 2015, if not earlier, we established jointly a lab called C-Lab that is physically located in the Navy premises in La Spezia. And you can see in this slide a couple of pictures of the location. Now, this is very important because from the Navy side, on top of the collaboration, let's say in terms of research, we can also benefit from their, let's say, competence and their know-how in terms of logistics and in terms of operational capacity of putting equipment into the sea. I think from all presentations, none excluded, that were already done before mine, you could very easily tell that the effort to put these assets in the water is usually very high, especially if you have more than just a couple of vehicles. The infrastructure and the logistics is extremely complex. So having the Navy supporting us in this respect is, of course, very important. Okay, this is again another slide with a number of topics that we cover: components and sensors, sensor integration and data fusion, individual agent autonomy. This means working on the autonomy of single vehicles. And then, as opposed to this, the multi-agent control, including cooperative autonomy and mission planning and supervision. And in between, of course, there is communication that is very important. Just one word, but I think an important one, about the role of the Genova University in this. As I mentioned earlier, the headquarters of ISME are hosted in Genova. And I must confirm that the university, in the last few years in particular, has had a very strong commitment to push for whatever, all the topics related to the ocean. So a few years ago, this Centro del Mare was established. That is an initiative to coordinate all the university activities dealing with the ocean. So not only in engineering, but also in all the other topics. So economy, law school, history. And this Centro del Mare hosts a very ambitious PhD program that is actually coordinating all these topics. So I find this very important, and I think it's useful for the audience to be aware of this. This slide, I think, is also interesting. It's a collection of the logos of the projects we have been following in the last maybe 15 years. So it doesn't include all of them because the older projects are not here represented. But I think it's good to convey the message of the number of projects that we have been working on. By the way, this is important. The center does not receive, let's say, basic research funding. So all our work is performed on funding coming from projects that are either European very often, or national projects, or even from the industry. Okay, I think this was mentioned already by Antonio, and so I will not say much. This is an ongoing project on sharing the infrastructure, and the ISME responsible for this project is colleague Gianluca Antonelli, sitting in the University of Cassino. By the way, Gianluca is the vice director of the center. And you see in the slide on the right the number of European labs and cities that are actually contributing to this effort. We find it was very successful, and we are hoping actually to have some kind of follow action on this. Regarding the individual agent autonomy, so as the word says, we work on individual vehicles, both underwater and on the surface. On the surface, this was shown already by Antonio, I think, in a previous presentation. In Genova, this vehicle was designed. The key person is Enrico Simetti. By the way, he is also sitting in this room, so if there are specific questions, of course, he can answer. It's an autonomous catamaran of the size that you see here, and the interesting aspect of this platform, there are several interesting aspects, but one that we exploited already in several occasions is the considerable payload capacity it has. So it can carry above, I think, 200 kilos, are reported in this slide, and this let's say, allowed us to use it, not in the WEMAS project, but there are plans to exploit it even further. AUV development and testing, so several of the nodes, for instance, Florence and Pisa in particular, have worked and are still working on design of vehicles. Typhoon class is a large AUV that was designed in Florence some years ago, designed and built. The same lab, together with other partners, along some projects that you see listed here, they designed also the Marta and Filippo AUVs that are smaller platforms, autonomous underwater vehicles. And these platforms are not the only ones we have. So the center also acquired over the years some vehicles from Graltech. This is an example. This was an, I don't know if it's an X300 or a Folaga. Anyway, it's an AUV that was used in La Spezia to do some research on energy harvesting from the ocean. So energy harvesting and energy management, energy-related issues, let's say, with the ocean, are one of the topics covered by the Institute and by the center. And in fact, the center also hosts a rather large infrastructure that is a wave generator used for energy harvesting experiments and studies. The responsible person is from the University of Genova in this case, and it's Alberto Traverso, who is responsible for this. There are very many other activities related to the single vehicle autonomy. I apologize, but let's say, for the sake of saving time, I will actually go fast on these. Just let me show you that we had several industrially driven projects related to aspects of navigation, guidance, and control of these AUVs. This is a specific one more related to communications. So the node in Calabria has worked and is working on the development of acoustic modems, low cost and low form factor for underwater applications in robotics. And then we have all the theme of cooperative control and cooperative applications. WEMAST was mentioned already many times today, and I don't want to bother people any further. I just want to mention that the web page of this project is still up and running, and there is also a YouTube channel where you can find, from ISME, where you can find specific videos related to WEMAST. And of course, if anybody has any other kind of question or interest, me, Antonio, Alessio, we were all on this project, and we can of course, provide more feedback. I put these pictures here just to convey the message that these kinds of activities, as was mentioned, I think by Antonio already, are very demanding in terms of manpower. So these large projects where you put a lot of vehicles at sea, even Alessio mentioned the same for their own company experience, they require a lot of work in terms of integration. This is even more so if the assets you put together come from different partners. So the effort of integration is very large, and you can see over the We Must project, but you could probably do the same with many other marine robotics projects. There are these pictures over the years where the number of people is rather impressive, and it's really necessary. We worked very late at night almost every time when we had experiments running. So this is something I think that should be mentioned. This is an older project related to cooperation, but I will not mention. These are now, I have a couple of slides on two very recent projects that are actually starting now by the node of ISME in Florence. One is this passport related to monitoring and improving security and safety in port areas using robots, autonomous robots. And the other one is called Pathfinder, that is financed actually by the European Space Agency. So space and underwater scenarios have very many similarities, and I find it interesting also to mention that funding itself may sometimes come from this direction. This is another ongoing project that is related to also flying robots, and the idea is to design a system whereas some flying UAVs can autonomously land on a marine platform, and this is, I think, also for future activities very interesting. I will skip these older projects, and I would like to go on something that was not mentioned yet today, but I think is extremely important, and namely what we call intervention robotics. What is intervention robotics about? Well, I think all, except maybe for the example Alessio Turetta made of the vehicle needing to have a close contact, coupling with the terrain, but all other acquisitions that we saw performed by underwater vehicles are, let's say, remote. So the vehicle senses either an acoustic signal or acquires images. So it has tasks that do not require necessarily a physical interaction with the environment. But in intervention robotics, refers precisely to the other situation, namely when a robot needs to have a physical interaction with the environment. So either picking up something from the seafloor or turning a valve in some kind of infrastructure. And this kind of work has been one of the topics of ISME since historically, let's say. We have had several projects, by the way, many, I would say probably most of them, in partnership with Graltech, who also has a very long track record and experience in this area. And this is one of a few years ago. I think I have a video from this one. Might be interesting just to have a quick look. Because this was a project where there was the autonomous recovery of a black box, or of an object. In this case, it was the black box of an airplane from the sea bottom. Now, what you don't see, the arm, if I'm not mistaken, was a Graltech arm, and the vehicle was a vehicle from a partner in Girona, in Spain. The hand is also from ISME, it's from the node of Bologna, that has a specific expertise in this field. What you do not see from this video, because of the point of view of the camera, is that the manipulation of this object was being performed floating. So usually the simplest way to operate a robot is from a fixed base. And this actually happens often when you land a vehicle on the sea bottom and then you use the manipulator for some kind of task. The alternative is to operate the manipulator from a moving platform, which is much more challenging. I will not go into the technicalities, but I think you can easily imagine the complexity of this. And the control systems to operate this were actually designed here in Genova, where there's a specific expertise in this. Okay, I have a number of other projects related to this. I think I will just simply skip these slides and point the interested people to our YouTube channel or the ISME webpage, where these projects are listed. The ones that I am quickly browsing now are recently ended. Recently means in the last 3 to 5 years, and they all have to do with manipulation. Dexrov, Robust, and Maris, that is a little bit older. Final note, diver assistance. This is, of course, the hot point and interest for H2O robotics. We also, in ISME, have an interest in these kinds of technologies, and in particular, there is the node of Ancona, the University Politecnica delle Marche, where they have this kind of research going on. Again, there are a number of projects that I'm not listing here, but I just wanted to mention that this is indeed one of the topics that is being followed by the Institute. The last slide I would like to show, and then I close, is a very interesting one. At least in my view, as a director, I just wanted to highlight that on top of the research that we do in the center, we also do a lot of training, and sometimes this is a little bit overlooked at, I think. In fact, being universities in the center and being academia, Antonio, I think, knows, and all the other colleagues from university, Pino, of course, and Enrico, very well know that a lot of our time is actually invested in teaching and in training, not only in doing research. And this, over the years, resulted in a very large number of master students who specialized in the field of marine robotics, very many PhD positions. I myself did my PhD within this, let's say, framework, as well as other people sitting in this room. We have Navy officers that came out of our experiences, and researchers both in academia and in industry. And another outcome of all this kind of work is spin-off companies. So there are several spin-off companies now running in Cassino, in Florence, in Rome, and if I'm not mistaken, even Graltech many years ago actually started as a spin-off. Of course, it's not a spin-off any longer because they are very solidly independent, but I think it's important to mention that the work we do can lead actually also to this kind of output. Sorry, I took 3 minutes more than I was expected to. I will close it here. Just leave my contacts and a link to our YouTube channel.
Elena contacted Vladimir. She's waiting.
I'm of course available for questions if there are any. I don't know if there is nothing in the chat. No. So, Massimo, we mentioned we could have a short discussion now. If there are no questions on our two presentations,
yeah,
I would just
I think we can also finish.
Yeah, I think we can
Yeah.
close this. Of course, please.
Of course, there
Go
are
ahead.
questions.
Are the rescue and intervention robots that you showed, are they fully autonomous in grabbing things as well?
That's a good question. Let's say the individual tasks are autonomous. So you can command, for instance, in the Trident case, there are flying to the location is one task, for instance, and then once you spot the black box and you need to recover it, once the vision system or whatever sensing system has identified the object to be grasped, you can launch another task that is autonomous. But it's not that you launch the vehicle from the port and it goes autonomously to find and get the building blocks to get to that autonomy are available. But in the case of this specific project, like in most research projects, usually the autonomy is at a lower level, let's say at a task level. So I don't know if this responds fully to your question.
And in many cases, as for instance in the case I showed before, when we collected this kind of coral spriozoi from the sea bottom, they are very fragile. It is very, very difficult, let's say impossible, to foresee their shape and everything. And so basically you can make it only in a teleoperation way, with a man in the loop for a visual feedback. And also you have to learn to design good end effectors in some way shaped for doing that tasks. Mm-hmm. And probably we would need, I was mentioning, dealing more with to say intervention robots for natural and especially biological objects to be manipulated, not for instance for if you have to rotate some device, to act on some device in an offshore system. But in those cases also to study and develop soft materials to be mounted on the end effector, able to be soft also in the presence of high pressure. So this is a great challenge for we studying materials, for instance, for the next years. So to have full autonomous manipulation underwater, it is something that we have to study more and more.
Yes, I agree fully. So I also don't want to keep people here more than necessary. I would just like to thank again the organizers, the Genova Blue District, for hosting us in this very nice location and for supporting the speakers that came from abroad. Also, we were mentioning during the break that at least to me, the session was was very interesting. I hope it was also for the audience and for the people following remotely. So I would like to thank again the speakers we had, Massimo and Antonio, Vladimir and Alessio. I think the lesson learned today is that we should find chances more often to meet in person, because these remote things actually are not the same. This is my impression. Thank you again to all, and if there are questions or oh yeah, just one last thing. We were supposed to have this demo session. The demo session was expected to be in multimedia format. Now, we thought to suggest actually watching our videos on the YouTube channels, but if there are remotely questions specifically, please let us know so we can give the links. And I would say that's all.
Thanks.
Thanks again to
Thank
all.
you very much also for the audience.